In this video I'll talk about the equations of motion. V equals u plus at, s equals ut plus half at squared, v squared equals u squared plus 2as, and of course s equals half u plus v times t. I'll show you how to derive all four equations, then go over some important points to remember. I've also made a video of worked examples, so take a look at that too. Sometimes these are referred to as SUVAT equations because of the letters used. S is displacement in meters, u is initial velocity in meters per second, v is final velocity also in meters per second, a is acceleration in meters per second, and finally t is time in seconds. Now it's important to remember that the first four quantities are all vectors, so for them direction has to be taken into account. I'll say more about this after going through the derivation. Here's the first. We'll start with an equation we already know from National 5, a is v minus u over t, and rearrange it to give the new equation v is equal to u plus at. It's a good idea to practice writing down these derivations yourself, so in the first line you'd write a is equal to v minus u over t. Eventually we want to get v to be the subject of the equation, but we can't do that all in one step. We'll start there. So in the second line we have v minus u is equal to at. If we add u to each side, we get v is equal to at plus u. So we can just rearrange the right hand side to give us the equation we're looking for. As I said, try writing out derivations with each step in the new line until you've memorised them. Here's the second one. This one involves a velocity time graph, and something else we know from National 5, the displacement can be calculated by finding the area under the graph. We'll use this to derive the equation s equals ut plus half at squared. Imagine an object accelerating uniformly from initial velocity u to final velocity v in time t seconds. The displacement s is found from the area under the graph. So firstly, we have this section, a rectangle. Its area can be found by multiplying its height by its length, giving us ut. The second section is a triangle. Its area is equal to half times the height times the length. The height of the triangle is v minus u, and its length is just t. So its area is half times v minus u times t. If we remember back to the last derivation, at one stage we had v minus u is equal to at, so we can substitute at into the brackets. If we now multiply out the brackets, we can get the equation we're after. For the third derivation, we start with the first equation and end with this. A squared equals u squared plus 2as. We start by squaring both sides, which gives us this. We then want to multiply out the brackets. There's more than one way of doing this, but we should end up with v squared equals u squared plus 2uat plus a squared t squared. Obviously you want to try this yourself. The left hand side of the equation looks fine, but this part, it needs more work. What we do is take out 2a from this part of the equation, leaving the rest in brackets. Dividing 2uat by 2a gives ut. If we divide a squared t squared by a, we would get at squared. So dividing by 2a would give half at squared. So the right hand side of the equation can be written like this. Go over this step again if you're not too sure. Now remember that our second equation was s equals ut plus half at squared. So the term in brackets can be replaced by the letter s, giving us a third equation. The last derivation is the simplest. We start with these two equations. The first says that displacement is equal to average velocity times time, and the second is an equation for average velocity v bar, which is half times u plus v. We then end up with this. S is equal to half u plus v times t. All we have to do is substitute the second equation into this position in the first, like so. To end the video, I'll go over a few final points by answering a question. Remember before that I said that s, u, v, and t were all vectors, and that only t was a scalar. That's very important when answering questions like this one. So the question says, a girl throws a ball vertically upwards with an initial velocity of 20 meters per second, then catches it sometime later. Calculate the time taken for the ball to return to the same height as it was released. Now in this question, I'm going to use something known as the sign convention. So I'm going to be taking as positive the upward upwards direction. Now, I've written that here in shorthand, but really what I should be writing at the start of this answer is something like this, taking upwards as positive. Now if I then write down what I know, and of course what I'm trying to work out, remember we said that these were known as Suvat equations. Let's see, now S, that's displacement, not distance. If it was distance, we don't actually know how far up the ball has moved to maximum height, and then of course the total distance, by the time it comes back to its starting position, its total distance would be twice the maximum height. This is displacement, remember. And of course, if it's returned to its initial position, of course the equation will be zero. Once again, using the sign convention, that anything moving upwards is positive, so initial velocity would be plus 20 meters per second. And of course that then means that final velocity v, since the ball's moving downwards, when it's at the same height, then of course we're assuming at this point that the air resistance is negligible. It has no effect. So of course, coming back to the same height, final velocity would be negative 20 meters per second. Acceleration due to gravity at 9.8, as you'll find in the data sheet at the start of the paper. But of course, when the ball's moving upwards in the positive direction, it's decelerating. That would give a negative acceleration. Then when it starts to move downwards, it's accelerating. So it's accelerating, but that's in the negative direction. So it's either decelerating in the positive direction or accelerating in the negative direction. Either way, that's an acceleration of negative 9.8 ms to the minus 2, when we're, of course, taking positive as upwards. The time we don't know. And it's a simple case of just working out which equation to use. I'm going to use v is equal to u plus at, and then, of course, substitute. V is